In the early 1900s, Seattle was a growing city hemmed in by geography. To the west was Puget Sound, a vital link to the Pacific Ocean. To the east, Lake Washington stood between the city and the farmland and logging towns of the Cascades. As the population grew, pressure mounted for a reliable east-west transportation route. But Lake Washington wasn't easy to cross. Carved by glaciers, the lake is deceptively deep, over 200 feet or 60 meters in some places. And under that deep water sits an even deeper problem, a 100-foot layer of soft clay and mud. Building bridge piers all the way to solid ground would have required staggeringly sized supports. The cost and complexity made it infeasible to even consider. But in 1921, an engineer named Homer Hadley proposed something radical, a bridge that didn't rest on the bottom at all. Instead, it would float on massive hollow concrete pontoons, riding on the surface like a ship. It took nearly 2 decades for his idea to gain traction, but with the New Deal and Public Works Administration, new possibilities for transportation routes across the country began to open up. Federal funds flowed, and construction finally began on what would become the Lacey V. Murrow Bridge. When it opened in 1940, it was the first floating concrete highway of its kind, a marvel of engineering and a symbol of ingenuity under constraint. But floating bridges, by their nature, carry some unique vulnerabilities, and 50 years later, this span would be swallowed by the very lake it crossed. Between that time and since, the Seattle area has kind of become the floating concrete highway capital of the world. That's not an official designation, at least not yet, but there aren't that many of these structures around the globe. And 4 of the 5 longest ones on Earth are clustered in one small area of Washington state. You have Hood Canal, Evergreen Point, Lacey V. Murrow, and its neighbor, the Homer M. Hadley Memorial Bridge, named for the engineer who floated the idea in the first place. Washington has had some high-profile failures, but also some remarkable successes, including a test for light rail transit over a floating bridge just last month in June 2025. It's a niche branch of engineering full of creative solutions and unexpected stories, so I want to take you on a little tour of the hidden engineering behind them. I'm Grady, and this is Practical Engineering. Floating bridges are basically as old as recorded history. It's not a complicated idea. Place pontoons across a body of water, then span them with a deck. For thousands of years, this straightforward solution has provided a fast and efficient way to cross rivers and lakes, particularly in cases where permanent bridges were impractical or when the need for a crossing was urgent. In fact, floating bridges have been most widely used in military applications, going all the way back to Xerxes crossing the Dardanelles in 480 BCE. They can be made portable, quick to erect, flexible to a wide variety of situations, and they generally don't require a lot of heavy equipment. There are countless designs that have been used worldwide in various military engagements. But most floating bridges, both ancient and modern, weren't meant to last. They're quick to put up, but also quick to take out, either on purpose or by Mother Nature. They provide the means to get in, get across, and get out, so they aren't usually designed for extreme conditions. Transitioning from temporary military crossings to permanent infrastructure was a massive leap, and it brought with it a host of engineering challenges. An obvious one is navigation. A bridge that floats on the surface of the water is, by default, a barrier to boats. So permanent floating bridges need to make room for maritime traffic. Designers have solved this in several ways, and Washington State offers a few good case studies. The Evergreen Point floating bridge includes elevated approach spans on either end, allowing ships to pass beneath before the road descends to water level. The original Lacey V. Murrow Bridge took a different approach. Near its center, a retractable span could be pulled into a pocket formed by adjacent pontoons, opening a navigable channel. But not only did the movable span create interruptions to vehicle traffic on the busy highway, it also created awkward roadway curves that caused frequent accidents. The mechanism was eventually removed